So I know you learned about the geologic timescale in physical geology, but it is a really important idea that we kind of make sure we understand. And plus, there will be times in the semester when you're going to want to come back to the geologic timescale and look at it. And so I thought I would take a couple minutes and kind of review it and sort of reconnect some of those neural pathways for you. So here is a version of the geologic timescale. And we're going to talk about how it's divided and maybe some of the words that you'll be seeing over the semester. This is certainly not the only version of the geologic timescale. Some get very detailed. Some get sort of in more detail as you focus in on a certain time period as well, with whatever rock layers you happen to be examining. So the largest unit of geologic time is called the eon. And there are 4 eons in the last 4.5 billion years of Earth history as divided by geologists. We're going to talk about what are some of the huge shifts in events that occurred over the eons that would make geologists, when they're interpreting the rock record, come up with a completely different eon. Like, why does one eon end and the next eon begin, for example? The first 3 eons in Earth history are collectively known as the Precambrian, and we'll talk about why in a little bit, but I'm going to give you a quick overview of geologic time here. The Hadean is the first eon in Earth history, and it basically is when Earth was in its infancy. It describes a time period when the Earth was initially molten and when the moon was created. In the early Earth history, there were very, very, very thin continental, or not even continental plates. By the end of the Hadean, there was the beginning of continental land masses, but mostly really thin plates on Earth. Plate tectonics was super active during this time period because the Earth, in its core especially, were very, very hot. But at the beginning of the Archean eon, we start to see the beginning of the setup of Earth. By that, I mean that there were oceans and there was the beginning of continents. And although the atmosphere was red because of a really high concentration of methane in the atmosphere, life evolved during the Archean eon. And there was very little free oxygen. Free oxygen really started to become common in the following eon, the Proterozoic eon. And that's because of the presence of blue-green algae that began to oxidize the atmosphere by absorbing a lot of that methane and carbon dioxide from the atmosphere and turning it into free oxygen. This resulted in huge climatic and atmospheric changes. So, sorry, my dog is snoring a little bit. I'm boring him. So methane is a super strong greenhouse gas, which means that it's capable of absorbing a lot of the heat that comes off and is radiated from the Earth. And so there was a really high concentration of methane in the atmosphere during the beginning of the Proterozoic. As methane, has the chemical formula CH4, as that was being oxidized to carbon dioxide, which is CO2, what began to happen was, first of all, a lot of the iron-rich rocks on the surface of the Earth rusted, but then eventually oxygen began to build up in the atmosphere, and this greatly changed the atmosphere. For one thing, the atmosphere changed from red, like we see on Mars today, to the blue that we're much more accustomed to. Secondly, because there was so much drastic reduction in greenhouse gas concentration, global climate plummeted, and there were multiple incidences of what geologists call snowball Earth events that occurred in the Proterozoic. And that's time periods when it's believed that the entire Earth was actually covered with ice. But however, at the very end of the Proterozoic, there was a really important biological change, and that is the evolution of multicellular life. And multicellular life is likely, its evolution is likely to have occurred because of the buildup of oxygen in the atmosphere, which is a really powerful fuel for organisms. So when I first went to school many, many, many years ago, geologists didn't know near as much as we do today about these first 3 eons, which comprise 85% of the history of the Earth. And geologists would collectively refer to these 3 eons as the Precambrian eon. And the Precambrian eon ends with a couple events, but really just the evolution of hard parts in organisms. So, like shells and teeth and bones become common in the fossil record about 542 million years ago, with the beginning of what's known as the Phanerozoic eon. So, you may remember from igneous rocks that the prefix "phan" means visible. So zoic means life. So the Phanerozoic eon literally translates to visible life, the eon of visible life. So eons are further then subdivided on the geologic timescale into eras. So let's look at the eras of the Phanerozoic eon. The Phanerozoic eon has 3 eras, the oldest of which is called the Paleozoic. So again, if zoic means life, paleo means ancient. So this is literally translating to ancient life. Mesozoic, meso means middle, so this is middle life. And then Cenozoic means modern life. Each of the eras is in the Phanerozoic is marked by an important biological change. At the end of the Paleozoic era, there is a massive mass extinction that is likely caused by the largest volcanic eruption that is known. During this mass extinction, something like 95% of everything that geologists know were alive went extinct in less than a million years. So a huge biological shift. At the end of the Mesozoic, through a series of certainly asteroid impacts and major climate upheaval, there is a massive mass extinction also. About 75% or more of all known organisms go extinct, and including most dinosaurs, non-avian dinosaurs, and then that ushers in the Cenozoic, which is really the age of mammals. When there are smaller but still significant biological changes, very often there will be a shift in period, and period is the next sort of subdivision of the geologic time scale. So between the Ordovician and the Silurian, there's a large glaciation that occurs, a large ice age that occurs, and there's a big shift in biology, or at least in the fossil record here, because a lot of shallow water organisms go extinct during the Ordovician to Silurian transition. And not shown on this geologic time scale, but on other geologic time scales you'll see our epochs. Epochs are shorter periods of time, and again, they just represent smaller environmental or biological changes. Jack, stop. I'm sorry. So a good example of an epoch would be like the Pleistocene epoch, which occurred between like 30 million and 10 million years ago. And during the Pleistocene epoch in the Cenozoic era, oh my goodness, in the Cenozoic era, the world was characterized by ice sheets in the northern hemisphere. So again, just a little quick review of the geologic timescale, and maybe bookmark this because it is something that we'll be talking about, and you just kind of want to know some of the terms from this just for reference in the future.